Hello everyone, my name is Wong Watana, and today I'm going to present about the discrete math, which is I'm going to talk about the application in cryptography. So basically, first we're going to know who am I. My name is Watana Wong. I study in the Department of Computer Science at Paragon University, and this is the course of discrete math. So first, I would like to begin with the number theory. Like it is nowadays, number theory is play as important role in modern technology, especially like cryptography. And moreover, this report is going to um, emphasize all of you about the RSA encryption. How is it really impression? So first, I would like to tell all of you about the number theoretical background. So the first theoretical that we're going to use, it is a prime and the fundamental of the theorem. And the second one is greatest common divisor, which is known as GCD, and last but not least, Fermat-Liouville theorem, and the last one is Bézout theorem. So with the first theory, the fundamental of theorem or of arithmetic on prime number, this is the form of the fundamental theorem of arithmetic. Sorry. So to understand this, we should look closely to the definition. Every integer greater than 1 can be written innately as a prime or a product of two or more prime, where prime factors are written in front of the least decreasing size. So for example, like 179 and 300. So 179, there are no anything that can product with it, any number else. But for the 300, we can see that it could be the prime factorization, like 2 times 2 times 3 times 5 and times 5. So it's not a prime. So the prime, it could be only can divide it by itself and number 1. So the theory 2, it is the definition of GDC, A and B. So now look closely to the definition, and this is the example of GCD. So this is find the GCD of 179 and 230. So the step 1, it's just the keyword of GCD of 179 and 230. So here it is. You can see the result of the GCD of this bunch of number, like 230 equal 179 times 1 plus 51, and this is called the GCD. And now let's moving on to the theory number 3. So the Fermat-Liouville theorem is a p prime as a, it an integer not divisible by p, then a to the power p minus 1 congruent 1 mod p. So this is the form of the Fermat-Liouville theorem, and the theorem number 4, it is a Bézout theorem. So if a and b are positive, then there exists integer s and t such that GCD a and b equal sa plus tb. So this is the form of it, and two of this we will cover it in the application because it's too long. And this, what is we want to talk about, like the RSA encryption. The first is type of public key cryptography, two based on the prime factorization and modular arithmetic. The third one is allow secure message exchange over open network. So now the important thing is became like we have one problem. So let's read it. Real life problem. Imagine that military A want to send a message bomb to another military B, but they do not want others to understand in word except themselves. So they need to use crypto systems, which is follow this step. So for the first one, we need to translate that plain text message bomb into a sequence of integer, apply RSA encryption to find a public and private key. The third one is encrypt the key. So here is the solution. So for the first one, we know that we need to translate a plain text message bomb into a sequence of integer. So we assume like a equals 0 0 and b is equal 0 1 and z equals 25. So here is the form of the bomb that we converted to sequence of integer. Like we can see that b is equal 0 1, o equal 14, m equals 12, and b equals 0 1 again. So the second step is apply RSA encryption to find the public and the private key. So to find the private and public key, the first step in this step, it must be choose two prime of number, which is you can choose a large as much as you can, even until it is a prime number. So but this is I choose the small because it's easier to explain. So we choose two prime number, p equal 11 and q equals 13. And why it is prime? We can apply the fundamental theorem of arithmetic to verify this one. And step B, we need to compute n equal p times q, and this is the result 143. After that, we find coprime, which is it is a RSA encryption. This is the form of it, and after we compute it, it's equal 120. You see, and we have another step in this step. We choose E, which is E GCD of E and coprime equal 1. So here E equals 7 and check. We need to check E and coprime, which is equal 120, need to be equal 1. And the step 1, we need to find like this form because we apply the GCD, and with this form we can apply Euclidean algorithm, and this is the form of the GCD, and the remainder equal 1. So the GCD of 7 and 112 is 1. So another part is to apply the Basel theorem to find D, and which is the modular inverse of E mod coprime. And based on the theorem, this is the form that I talked a moment ago, and I just convert or change the letter S to D because it's easier to see. Yeah, and this is we apply the Euclidean algorithm again, but we need to use the this one to use the inverse. So 1 is equal 120 minus 7 times 17. So we can see that minus 17 times 7 congruent 1 mod 120, and we can write it in another form. So D is equal 130 because minus 17 mod 120 equal 103. So after that, we can see the public key and the private key. So the public key is E equals 7, N equal 133, which is for military A to encrypt this message, and the private key for the military B to decrypt this code. And this is the form that we have, like we can encrypt the code. So this is for the military A for encrypt the code. Like we can see as the form, we can use 0 1 to the power 7, which is E mod 143, and it's equal 0 1, and it is the new one. And this is the following step because it is the same as you can see, and all of these numbers are encrypted. And the military A is going to send that message 0 1 53 12 and 1 01 to military B to decrypt it, and the private key, it is this one. So we need to must understand that we keep this code is really important. And after the military B decrypt this code like 01 to the power 1 and 3 mod 143 equals 01, which is B, we known as B, and the following step is a 14, 12, and 1, and it is the same. So the military B will understand that it is the word bomb, which is really the secret one. And now my presentation is come to an end. I would like to tell you, conclude about this, that it's really RSA encryption is really important in technology nowadays, and I want to understand more in the future, more emphasize about this, because I'm really interested about this. And thank you so much.